Good morning, good afternoon, or even good evening to all the participants that just joined us. I know that they are scattered across the globe. You're very welcome to the highlight talk on the solid Earth and its structure. We are, I think, particularly benefiting today to have one of the most influential seismologists of this times with us today to give us a presentation on imaging the Earth's deep interior using seismic waves. And of course, I'm talking about Barbara Romanovic, who's joining us from France. Barbara holds a PhD in geophysics from the University of Paris 7 in France between 1982 and 1990. She worked as a researcher at the Scientific Research National Center in Paris, where she developed Geoscope, a global network of digital seismic stations from the study of earthquakes and the structure of the Earth's interior. In 1991, she was appointed as the director of the Berkeley Seismological Laboratory and professor in the Department of Earth and Planetary Science at the University of California, Berkeley. During her directorship, she helped establish a joint Berkeley-US Geological Survey real-time earthquake notification system for Northern California. Her research interests include the study of deep earth structure and dynamics using seismic data analysis and modeling. Among the honors that she has already received, she was elected to the US National Academy of Sciences in 2005 and was appointed to the chair of physics of the Earth interior at the Collège de France in Paris in 2011. She's the 2019 recipient of the AGU William Bowie Medal. And also in 2021, she received the ISPA medal. So as I think we already know, Barbara has studied the Earth from its surface right down to its center. And my name is Gerald Graham. I'll be convening the session, and with me is my colleague, Joseph Villa, who will be handling all the questions that will be coming our way. So thank you. And Barbara, I'm going to hand over to you. Please proceed.
Thank you very much, Graham, for this nice introduction. I'm very excited to present a review of my research field to all of you. I hope it goes well. I'm in the little village in the middle of nowhere in Burgundy, and internet connection isn't that great, but we'll try. So just to get started, the field of global seismology was born somewhat over 100 years ago when von Reuber-Paschwitz was measuring tilts of the Earth due to Earth tides at two places in Potsdam in Germany and in Wilhelmshaven, and he noticed an unusual disturbance. And a couple of months later, he read in a Nature journal that there had been an earthquake at that time, and he thought, well, that's quite a coincidence, and figured that it was the waves excited, the seismic waves excited by this earthquake that had traversed the Earth and were recorded on these instruments. Nowadays, of course, we know that seismic waves do travel through the Earth, and the seismic wave field interacts with the different boundaries, the different discontinuities within the Earth, producing reflected waves, which can be registered in different seismic stations. And for 100 years, seismologists have analyzed these records, made record sections as a function of distance to recognize which waves went which way through the Earth. And here on the right, you see a seismogram that is about an hour long, actually just 50 minutes, showing the succession of waves that arrive at a particular station. These waves are of two kinds, of course, compressional and shear waves, and some of them traverse the Earth through their interior, which are called body waves, and then the surface waves have their energy confined to near the surface. And we can use these seismic waves to image the Earth's interior as the velocities through the Earth's interior changes depending on what material they encounter. Also, if you look at a very long record, here we're talking about 15 hours on this particular plot. For very large earthquakes, you see a succession of waves, surface waves in this case, long period surface waves that have traveled in different directions around the Earth. And you see at a given station the different arrivals that decay with time slowly because the Earth is not perfectly elastic. And if you take a spectrum in the frequency domain of this record, you will find peaks that correspond to the characteristic normal mode frequencies of the Earth, which also carry information about its internal structure. And so using these informations from the travel times of seismic waves traveling through the Earth's interior and from the normal mode frequencies, seismologists over the years in the 20th century up to the 1980s with models of average models of the Earth's internal elastic structure. We are fortunate that the Earth is to a very good approximation spherically symmetric, made up of concentric shells. And so a so-called 1D, only dependent on the radius model, is a good first approximation. And these models describe the shear velocity dependence with depths, the compressional wave velocity dependence with depths, and also the density, which is harder to get directly from seismic waves. The best way to obtain it is from the normal mode frequencies. And these velocities and density were confronted with information from mineral physicists that then established the average composition of the different layers of the Earth with its solid silicate mantle, liquid iron, primarily iron core, liquid in the outside, and then a solid inner core. The structure reflects, has some complications, in particular in the upper mantle, which we call the transition zone. We have two sharp discontinuities, which correspond to phase changes in the mineral olivine, which is the main constituent of the upper mantle rocks. And then we also have an interesting layer we call the D double prime layer right at the base of the mantle, where the behavior of the velocity tendency with depth changes, and which turns out to be a region of complex structure. Now, this is a very static view of the Earth's interior, and what we're interested in is its dynamics. We know the Earth is dynamic. It goes back to Wegener and the continental drift. And nowadays we have accepted for now more than 50 years that we have plate tectonics, and the plates are moved by convective currents inside the mantle. The mantle is solid, but it is solid for the propagation of waves through it, for the propagation of seismic waves. Instantaneously it's solid, but over long times it flows, and the mantle viscosity is drops quite dramatically from the lithospheric plates to the upper mantle, the region called the asthenosphere, and then increases with depth down to towards the core mantle boundary. These are just cartoons indicating what the convection currents might be like, but this is really the question we want to answer with seismic imaging, is what is the morphology of these currents? How do they couple with the plates? How do they drive the plates' motions? And such things. So for this, we use the we develop methodologies which are simply based on tomographic methodologies, where we want to detect currents that are going to be rising, are going to be hotter than average, and currents that are going to be downwelling are going to be colder than average. And this will be reflected in the velocities of the seismic waves, which will be faster when they traverse colder regions and slower when they traverse hotter regions. Now, this is the color scale that we use, sort of intuitive, with red colors indicating hotter and blue colors indicating colder. To a first approximation, we can interpret images of velocity of seismic waves as they traverse the medium in terms of temperature. But of course, this is only a first order interpretation, because composition may also play a role. And to remember, the main principle of tomography is that you want to have illumination from many different directions in order to be able to locate the anomalies and also determine their strength. Now, in global seismology, we have a challenge, because the sources of our of the waves, of the illumination of the Earth, are the earthquakes, and earthquakes are not distributed uniformly around the Earth. They are primarily occur on the plate boundaries, as you can see here from this distribution of earthquakes over a 10-year period, the colors indicating the depth of the earthquakes, which go down to about 680 kilometers depth in subduction zones. And also, the distribution of seismic stations is not uniform. It follows to some extent or to a large extent, the distributions of continents in the world. And of course, since 2/3 of the world is covered with oceans, we have fewer stations in the oceans. We go to islands. The idea of putting stations on the ocean floor is still not so much a technical challenge, but a very expensive challenge. And you can see just from this slide showing the broadband seismic stations that have contributed to the Federation of Digital Seismic Networks last year, that the distribution is very non-uniform. On the side, I show here a picture of the Cadillac of very broadband seismometers, which has played an important role in the development of tomographic imaging in the last 30 years. So here is a map at a particular depth. We are at 100 kilometers depth beneath the Earth's surface. And this is one of the very first tomographic models of shear wave velocities that was developed in the early 1980s. I show this model because it shows some very striking features. You see the slow velocities corresponding to the ridge system here, indicated in yellow. And you see the faster velocities corresponding to the old cores of the continents. You also see an increasing velocity going from the ridge towards the older parts of the Pacific. And this corresponds very well with what we would expect from plate tectonics, from the spreading of ocean crust at ridges. And you can see the age dependence very well, the cooling of the lithosphere going from the ridge towards the old parts of the ocean, and the colder than average older continental cores. So this was important because it showed, on the one hand side, that tomography works, that this kind of imaging of travel times, in this case, mostly of surface waves and their overtones, works well. And on the other hand, retrospectively, it was one more proof that plate tectonics exists. Now, this is from the same group at Harvard University 25 years later. And you can see the resolution is better. We see more details, but that the main features are were already present in the first tomographic models. Another aspect of imaging, besides just travel times of seismic waves, is that they can detect anisotropy. That is, that the waves travel at different speed in different directions. And these are examples of a recent model showing the azimuthal anisotropy of surface waves, that is, the variation with azimuth in the horizontal plane of these waves, where the red bars indicate the direction of the fast axis of propagation, and the length of the bar indicates the strength of the anisotropy. And you can see that the pattern changes from shallow depths here at 50 kilometers to a slightly deeper depth in the upper mantle. And it reflects quite well what we expect from interpreting the anisotropy as being due to the alignment of olivine crystals, which are themselves anisotropic, in a flow, either a faucet flow, so a flow that existed back in geological times. For example, here in the old Pacific region, you see the directions reflect what the directions might have been at about 150, 180 million years ago. Whereas if you go deeper, you're in the asthenosphere and you see the current direction of flow in the upper mantle. So combining, going back, I'm not going to talk more about anisotropy, but going back to simply the anisotropic part of the velocities, if you combine different types of waves, the surface waves, which are more sensitive to the upper mantle, and the body wave travel times, which are more sensitive to the lower mantle. Here we see on horizontal is depth from the surface on the right to the core mantle boundary on the left. And the red colors indicate a strong sensitivity of particular types of waves that are given here in the vertical direction. And so the surface waves gives you good resolution in the upper mantle. The body waves are needed to get resolution in the lower mantle. And when you combine everything, you can image the entire mantle. And so this is what has been done in the last 30 years. Here is a relatively recent model for the same. I showed the top figure from Harvard University. And you can see these maps at different depths. And as you go deeper into the mantle, the images change. What is striking to begin with is that the organization of these maps seems much more coherent at long wavelengths at the top of the mantle, 100 kilometers depth, and at the bottom here, which we are here about 100 kilometers above the core mantle boundary. And this is reflected in the spectrum of heterogeneity. The shorter the wavelengths, the angular degree indicates the shorter wavelength. This is spherical harmonics expansion of the structure. And you can see these strong peaks at low degrees, long wavelengths, both at the top and at the bottom of the mantle, which is reminiscent of what you expect in a convection system encompassing the whole mantle with two layers, one at the top and one at the bottom. So now let's look at this in more detail. As we go deeper in the mantle, we lose this signature of the plate tectonics. And here at 600 kilometers, I've also, in addition to the maps, I show depth cross sections. So it's basically a cross section diving into the mantle from the surface to the core mantle boundary in two different places here in Japan and in South America. And what you see here is the specifically in Japan, the Pacific plate, Pacific tectonic plate, going down back into the mantle. The cold, it's cold, and it's therefore imaged as faster than average velocities. If you see the white dots, I don't know if you see them, but these are earthquakes. These are Benioff zones of earthquakes going down into the mantle. And the striking thing here is that these subducted slabs don't continue straight into the mantle. They actually pond at around 660 kilometers depth, which is the boundary between the upper and the lower mantle, which corresponds also to a phase change in the olivine system, the decomposition of the olivine into perovskite and oxide. And as we go deeper, you see that the strongest features here are in the Fiji Islands and in northern part of South America, and in cross sections from another model that was developed using travel times of P waves, which are very which provide very good illumination in subduction zones, you can see that in some areas, these slabs pond deeper, more like about 1,000 kilometers, which to this day is very surprising, because even though we know there is a physical discontinuity, a phase change around 660 kilometers, there is no consensus right now about what physical cause might be at the origin of this ponding. Now, as we go deeper, near the core mantle boundary, the picture changes completely and is now dominated by a ring of fast velocities going through the North and South Pole and surrounding two regions of lower than average shear velocities, which has received the name, rather barbarian name, of large low shear velocity provinces. This structure has fascinated geophysicists, seismologists for quite a while now, and is still a subject of debate. So I will spend a few minutes on it. Again, here the same figure. And if I extract only the longest wavelengths and present it in a 3D rendering view, you can see this ring of fast velocities going through the poles with the equatorially and antipodally located large low shear velocity provinces. Moreover, if you plot the positions of the poles of rotation of the Earth in the past 250 million years, they plot in this ring of fast velocities, which seems to indicate that this structure is stable. It's actually stable from the point of view of the moments of inertia of the Earth. So one can think that perhaps in the past, when the lower mantle was not as viscous as it is right now, it might have been sensitive to the Earth's rotation, and position these structures antipodally and equatorially. Moreover, this kind of features is consistent with what you would expect from a simple convection, so-called degree 2 convection in a sphere with two upwellings, antipodal upwellings separated by a ring of downwellings. And so we have all these questions about the LLSVPs. They may have been stable for at least 250 million years. It's hard to go back further. We know also from other evidence that they have sharp edges. They maybe have a distinct composition. They may be denser than their surroundings. There is a lot of debate about it. And there are questions such as, how big are they? How high do they extend above the core mantle boundary? And what role do they play in the global mantle circulation? So we have a series of cartoons that are being debated at present, whether the LLSVPs are compact, high, tall piles, stable or metastable, or kind of breathing domes or superplumes, or are they simply a collection of mantle plumes? So this brings me to the subject of mantle plumes, which fascinates geoscientists. And so why is that? There are so-called hotspot volcanoes, such as the volcanic chain of Hawaii, which do not fit in the general plate tectonic theory, where you expect volcanism to be restricted to boundaries of plates, either mid-ocean ridges where new crust is formed, or in subduction zones where a plate goes back down in the mantle. And Hawaii is puzzling, not only because it's in the middle of the Pacific plate, but also that the volcanic chain has increasing ages, here indicated in millions of years, as you go, of course, extinct volcanoes. The currently active volcanoes here are 0 million years. And as you go further in, along the direction of the motion of the Pacific plate, the ages of the extinct volcanoes increase. And Tuzo-Wilson, at the time of when plate tectonic theory was being proposed and discussed, proposed a model for this, that model of a fixed plume of hot material somewhere in a boundary layer inside the Earth that would over which the plate would be moving, and therefore successively you would have extinct volcanoes in the direction of the plate, and new volcanoes would be formed above this fixed hot plume. And then Jason Morgan proposed a few years later that this boundary layer could be the core mantle boundary. And so why this plume idea? Well, first of all, there is the evidence that the hotspot volcanism is different from what is seen in mid-ocean ridge results. Here, in trace elements, neodymium samarium plot, but also in the proportions of helium-3 to helium-4. And there is also evidence from experiments in the laboratory and numerical experiments such as the one I'm showing here, which indicates that if you have a fluid heated from below, you will start seeing rising narrow plumes of hot material with big heads that rise throughout the volume of your system. Hotspot volcanoes are categorized, and we have about 50 that are the principal ones, and most of them are located in the ocean basins where tomographic resolution is poorer if we really want to see them. On the right here, I show an example of the so-called checkerboard test, where you input a full checkerboard encompassing the whole Earth, here shown at different depths in the mantle, and then you push it through your inverse process, through your tomographic process, and see what comes out, and showing clearly that with P waves, you cannot really resolve the structure very well in ocean basins, and certainly not in the southern hemisphere. So what can we do? There is another issue, which is that traditional tomography uses travel times, and travel times of first arriving waves. But if you have a relatively small object of lower than average velocity, the first arriving wave actually goes around the velocity, so it's hidden. The velocity anomaly is hidden from view. In order to really see it, you have to go deeper into the waveforms. You cannot use only the first arriving time. And so the methods have been developed over time to take into account the fact that the infinite frequency theory that was used previously to relate travel times of body waves and surface waves actually to the velocity structure needs to take into account the fact that the waves are broadband, that is, they have finite frequency, and corresponding kernels have been developed to account for this. Also, some efforts have been done to increase the aperture of arrays, seismic stations around hotspot volcanoes, like this one in Hawaii, the so-called Hawaiian Plume project, which used finite frequency kernels and came up with images like this, which here are shown in map view at two different depths in the mantle, 200 and 900 kilometers. And here are two depth slices in two different directions, northwest and southwest. And you can see that below the Hawaiian island, you can see this structure of lower than average velocity that seems to extend quite deep, certainly throughout the upper mantle, and possibly deeper. But this has been controversial because the aperture is still not quite large enough, and a lot of the ray path is not under the array, even if you have all these ocean bottom stations deployed at great effort several hundred kilometers away from the islands. There could also already still be some smearing coming from the part of the rays that do not contain any crossing paths. So what is the way to go? Well, the way to go is to try and increase the illumination that we have of the interior of the Earth by incorporating not only the arrival times of the main seismic phases, but the information contained in the entire seismogram, which will contain all these waves interacting with the core mantle boundary, the surface of the Earth, and other discontinuities in the Earth. And this leads to the concept of full waveform tomography, where now we consider an entire seismogram, so the complete succession of waves arriving following an earthquake at a given station, and compare it to a modeled seismogram in model Earth to try to improve this model Earth, this Earth model. Now, the issue is, how do we compute these synthetic seismograms? We have good methods to compute them in a 1D Earth, in an Earth where the structure varies only with radius. And we have for many years also used normal mode perturbation theory to compute 3D propagation in a 3D Earth. However, with making strong assumptions on the structure of the Earth. And only in the last 10, 15 years have we had a tool that allows us to compute these synthetic seismograms in a very accurate manner without without practically approximations on how strong the lateral variations in structure should be, or how smooth they should be. And this method is, of course, a numerical integration of the equations of motions, and the method of choice for global seismology is the spectral element method, which has the advantage of being, has several advantages, but in particular, it is relatively fast computationally. It is still quite heavy, and therefore progress in this area has been relatively slow. But it offers the hope of improved resolution, in particular for shorter wavelengths, low velocity features. So now I'll illustrate some of the recent progress. It is, of course, work that is still in progress, and we're still trying to improve the resolution. The community is trying to do that. But I'll show you an example here of these are cross sections across a whole mantle model, S40RTOS, developed 10 years ago by and collaborators, using classical travel time tomography, combining surface waves and body waves. And you can see in this picture, which is these cross sections across half of the Earth circumference between the core mantle boundary and the surface. You see these features that seem to indicate lower than average velocity, but they're not very clearly defined. And skeptics, if you like the idea of plumes, you would say, well, there is a plume going through here. But if you're a skeptic, you might say, well, it's not clear. We have other things going on here. And so this is not clear. Now with the full waveform tomography, we have a better view. And in fact, on the same cross-section, we can confirm that these features correspond to what we would call fat plumes. They are much broader than what you would expect from a simple model of the Earth's mantle as a fluid heated from below, but they are there, and they appear to be rooted at the core mantle boundary in the relative vicinity of these two hotspot volcanoes in the southern Pacific. We see these features in the Pacific Ocean and in the vicinity, rising from the core mantle boundary in the vicinity of hotspots. And we see them also in the African hemisphere, corresponding to hotspot volcanoes over the so-called African LLSVPs, as you see here, Cape Verde, Canary, Iceland, and in the south of Africa. They appear as quite fat structures, columns. In these images, they are about 1,000 kilometers wide. They may not be as wide because the resolution is still not perfect, but they are certainly not as thin as 100 or 200 kilometers that would be expected from a purely thermal convection. And they also seem to be separated from each other, even though this is only hinted in these images, and further work needs to be done to confirm this. They have some characteristics. They're rooted in very slow regions in the at the base of the mantle. And in fact, inside these routes, these routes correspond to about velocity reductions of about, say, 3% in shear velocity. But inside some of these routes have been found even more extreme structures that are called ultra-low velocity zones. Now, this is I'm just showing one example. This is not tomography. This is forward modeling of waveforms, very specifically waveforms of waves that diffract along the core mantle boundary. The background here is a tomographic model, and the ray paths here show the ray paths of the diffracted waves, with the green indicating the part of the path that is in the last 200 kilometers of the mantle. And as you look at, as a function of azimuth, from north to south, you see the observed these observed waveforms, which are filtered between 10 and 20 seconds period, having very striking kind of appearance. The amplitude decays of the main diffracted waves, and the travel time is longer, which is explained by the presence of the LLSVP. However, there appears this so-called post-cursor, at least 40 seconds after the main phase, which cannot be modeled even in a tomographic, the best current tomographic model of the Earth. It will not show anything like that. In order to explain this, it turns out that this is basically a diffraction pattern, a portion of a diffraction pattern, which would be a hyperbola, corresponding to a length of very slow velocity with a velocity reduction an order of magnitude larger than what you get from tomography, about 20% in this case, of this feature, which is also quite wide and turns out to be right at the base of the Hawaiian plume. There is similar observations that we have made under Iceland, where we have a better illumination of these features. And I just wanted to show you the, for those of you that like seismic waves, the features that you see. Again, these are the observed features as a function of azimuth, colored by the color, well, from blue to red, colored by azimuth. And you can see again these features of decreasing amplitude and the hint of this diffraction hyperbola, which you cannot see in the when modeling just a tomographic model, and you can model by introducing this kind of very low, ultra low velocity zone. Other ultra low velocity zones have been found in the world. These are not the first ones, but these are the first really large ones, which also seem to have a relatively circular pattern, but I don't have time to go into those details. Now, one more thing about these plumes or these columns is that they seem to be offset in many places, as they're very vertical from the core mantle boundary to about 1,000 kilometers depth, and then they are offset in the upper mantle going towards the corresponding hotspot. Sometimes you, because very likely they are thinner and below the resolution of these models. And this is reminiscent of what you might expect in a thermochemical convective system with a change in viscosity at some level, which here in this numerical simulation was chosen to be 660 kilometers because of the phase change at this depth. But in reality, it seems that the deflection is deeper, more like 1,000 kilometers depth, which again is this question of what is going on at this depth. So now I will, to finish, I will quickly go through and show you some images of one particular region in the Pacific of these plumes, this cluster of plumes from the core mantle boundary to the and here you can see a number of hotspot volcanoes, and we'll be looking underneath, starting at the core mantle boundary. So at the core mantle boundary, you have these very pronounced features with minima in velocity, And as you go deeper into the mantle, you see this formation of these columns. You can follow these columns all the way up to the upper mantle. And now I'm looking from the top, the same as previously. Sorry. Now I'm going to take this picture and turn it around to look from the top. And I can see these columns rising in the vicinity of these hotspot volcanoes. And seen from the south, now in the upper part of the mantle, the connection with the near surface structure is interesting because you see these elongated horizontal structures. The top one is the well-known low velocity zone, but there's another one underneath, which is intriguing. And in fact, if you look at it from standing on the East Pacific Rise and looking towards the west, you see these kind of periodic corrugations. The plumes seem to be feeding the system of corrugations of lower than average velocities that are aligned periodically with a spacing of about 2,000 kilometers. We can see these everywhere in the ocean basins. This is, again, a map view at 250 kilometers depth of a recent upper mantle model, which shows these elongated features that appear to be elongated in the direction of absolute plate motion. What I'm showing here is in broken lines are the absolute plate motion directions, and you can see these features both in the Pacific plate, but also in the slow-moving Antarctic plate, and also in the Indian Ocean and in the Atlantic. And so the question is, what are we looking at? Are these reminiscence of, they are reminiscence of viscous fingering experiments, where if you have a material of lower than average viscosity coming into what we would call an astenosphere, it forms these flower-like structures. And if you have a boundary that is moving, an upper boundary that is mobile, these petals will align with and opposed to the direction of motion. But it could also be so-called Richter rolls. This is secondary scale convection in the upper mantle that would be generate motion of the plate with the axis of the cells aligned with the direction of plate motion. More recent, these features that you see in the seismic models are also seen in the gravity field. Here are two figures of work, of a very recent work that I've been collaborating on, which is basically an analysis of the gravity gradients from space, from satellite measurements, from the GRACE data, and also the seafloor slope gradients, which indicate strength, energy in these data at the same wavelengths, in the same direction as in the seismology. And what's intriguing is that the correlation is actually opposite to what you might expect from a simple dynamic thermal model. And here is a picture showing a plume arriving in the upper mantle along this depth profile here from the surface to the core mantle boundary. And as it arrives in the upper part of the mantle, it kind of connects with these periodic features that cannot be explained by purely thermal anomalies, because the sign of the correlation between the gravity and the seismic data is opposite to what you might expect in a dynamic, purely thermal mantle. Okay, thank you. I'm almost done. Yes, and you see this in other plates. And so this brings me to a sort of a first conclusion, which is my view of the Earth mantle, sort of the working hypothesis, which we are continuing to try to refine, with a very sluggish circulation in the lower mantle, very viscous lower mantle, plumes rising very vertically, not affected by the global circulations, blobs of slabs falling quite vertically, and then a much more vigorous convection in the upper part of the mantle, which would encompass the first 1,000 kilometers of the mantle. And then in the root of these plumes, you might have these larger or smaller ultra-low velocity zones at the very base of the mantle. And one of the questions, main questions remaining, one of the most intriguing questions among many is what is going on at this 1,000 kilometers depth, where you see both slabs ponding and plumes deflecting at this depth. And so a number of questions are still open, you know, about the LLSVPs. Are they bundles of plumes? I think they are bundle of plumes, but I haven't proven it completely. Do they all contain these ultra-low velocity zones at the roots? What are they? Is this partial melt? Is this enrichment in iron? Is there a layer of primordial material at the core mantle boundary that would be tapped by the plumes? Or can this signature of the mantle, signature of the hotspot volcanoes come from the core? What is happening at 1,000 kilometers depth? We've already said that. And also from the latest intriguing results, do plates drive secondary scale convection in the upper mantle, or is it the other way around? So the way forward to finish, well, we definitely need more observations in the oceans. This is an effort that has been going on for many years, for many decades. Initially, the idea was to put permanent stations on the broadband stations on the ocean floors. This is an example of seeing where these stations might be the most useful, which parts of the ocean most useful. This turned out to be very costly and very technologically challenging and never really happened, although a couple of holes were drilled, one here on the on the 90th ridge in the Indian Ocean, and one offshore Hawaii, etc. The more modern view is more light experiments with broadband arrays deployed for temporarily for durations of 1 or 2 years, enough to record enough earthquakes. My wish would be that these would be much larger aperture, but again, this is extremely expensive and challenging. Another possibility is that kind of attempted now by the Mermaids program led by Princeton University and the University of Nice, where they send floats with hydrophones that record the pressure generated by earthquakes. They hang deep right above the seafloor, and they pop up occasionally to send data by satellite. And here is a picture showing the kind of resolution with P waves, because these are primarily first arriving P wave detectors, at least for now. You can see the resolution you can get with the current distribution of standard stations, primarily on the continents and on ocean islands, and what could be achieved with 1,000 mermaids covering all the oceans. So this is from the point of view of data acquisition and instrumentation. Now, there is also methodology which is being developed. One of these is the concept of tomographic. It's maybe not such a great name, but the idea is that computation of the seismic wave field using numerical method is extremely expensive, especially at teleseismic distances. And the idea is to focus on a region of interest in the deep mantle and replace a distant source like earthquake by a collection of sources around the region of interest using the principle of time reversal mirrors, and compute the complete seismic wave field only once in a background model, and then iterate inversion or tomographic inversion only in the region of interest, which could be very fast and allow us to go to high frequency, and using some regional solvers. And this has been, this concept has been proven in 2D, in a 2D Earth with acoustic, in a 2D acoustic Earth with a realistic depth dependence of structure, showing that even if you assume the background model is a 1D model, and you compare here the inversion in the entire mantle for a target model, which is indicated here, you can do the same with doing the tomographic inversion only in the small target region. And in fact, you get a somewhat better resolution by doing it this way than by doing it over the whole Earth. So this is sort of the promise of the future. And there are, of course, others that I haven't had time to discuss. And I would like to thank you for your attention, and we'll be happy to take some questions.
Thank you very much, Barbara. This was, I think, really the time went so quickly. We were just hanging on to everything you say in all the slides. And I can tell you that already in the chat, you would see several of the participants expressing their appreciation for your presentation. I think you can turn on your video.
Okay.
The connections, even though you said you're in a remote part of France, I think the connection held very well. Thank you.
Okay, I will leave my slides on in case I need to go back, maybe. I don't know.
In case you need to go back. So let me get to one of the first questions that came in. It says, do you think that convection nets inside the upper mantle do exist? And then it's a second part to that. Do you think vertical plume propagation nature is due to thermal differences between the upper and lower parts?
Okay, so the first question is about the presence of convection in the upper mantle. Yes, we definitely, we know there is convection in the upper mantle because this is what's driving the tectonic plates. We do not know exactly how the convection itself is coupled to the rigid tectonic plates. This is something we want to understand, but it is pretty clear that that there is convection. We have evidence for currents rising under mid-ocean ridges and diving in subduction zones. We have this evidence from seismic currents. We have evidence from seismic velocities. We have evidence from the anisotropy also. All of this points very clearly to the presence of convection in the upper mantle. Now, the plumes, as I explained, the classical model of a plume is in the context of a model which is heated from below, of a box convective system that is heated from below and cooled from above. But the plumes that we are observing in the Earth seem to be a little more complicated. They don't have the shapes, they don't have the thickness that you would expect. Scaling, you know, if you do scaling arguments to the size of the Earth and its properties, you would expect plumes of about 200 kilometers diameter. But what we see is much wider. The resolution is not perfect, but they have to be wider than 400 to 500 kilometers. Otherwise, if they were really narrow, in order for us to see them with the present resolution, they would have to be extremely hot. Like the contrast between the plume and the surrounding would have to be more than 1500 degrees or 2000 degrees, which we know from simple calculations and simple information that we have about the temperatures within the Earth and the lavas, from the lavas in the, that have been analyzed, that this is much too hot. So it's thermochemical convection. That is, it's a mixture of thermal effects and effects of compositional variations.
Thank you. If we go to the next question, can attenuation structure at the higher frequencies, less than 20-second period, can that help?
Well, actually, there are also models, I didn't talk about them, attempts at modeling the attenuation structure of the Earth. That is absolutely, would be very helpful, because the attenuation, that is the decay of amplitudes with distance or with time is depends on temperature primarily in an exponential fashion, and depends differently than the velocities, which are you could distinguish between the effects of temperature and composition if you had accurate maps of attenuation. So far, the primary attenuation tomography has been done only for the upper mantle and primarily using long period surface waves. Using body waves at short periods is much more challenging because there are many perturbing effects in the amplitudes that are due to simply propagation in a complex 3D elastic structure. And even though these complexities also exist for surface waves, they are somewhat easier to deal with than for the shorter period body waves. But I didn't show any maps. My group has been working on this. Many other groups have been working on this. But right now, the resolution we have in attenuation is much lower than in velocity because of this issue of perturbing elastic effects, which result in focusing and defocusing of energy. And you have to separate them is a challenge. You would have to know the elastic structure much better than we do.
Thank you. So I think the next question can probably keep you busy for another hour, but maybe briefly, there's a question that says, I'm interested in how you computed the data because I did a 3D tomography and it's Simulx 14. It says yours was very detailed. Do you want to say anything about your computation?
Well, yes, that could keep me very busy. I think the main point is that we're using the entire seismograms. And even though right now I didn't talk about the period range, but we go down to 40 seconds period only. The fact that we use the entire seismogram, which contains information about waves having bounced all over the Earth's mantle, combined with the fact that we can simulate them, we can compute the predicted wave field in an existing 3D model very accurately, allows us to look deep into the coda of the main phases and therefore have access to details and therefore increase resolution, especially resolution in the low velocity regions, which otherwise can be hidden from view from the first arriving waves.
And Barbara, the last question, and I think I have also a bit of a personal interest in this question because I know the debate that we often had in Southern Africa about the sort of comparison between the super swell and the super plume. And then there's a question that says, some argue about the ability of seismic tomography to provide us with great resolution at these very large depths, and suggest that these features may not even exist. So in short, the question is, do you expect any surprises in future? We have a breakthrough in data and methodology advances in what you are suggesting, in other words, your models in particular. Do you think anything could come later?
Well, first of all, about what we already see, I've shown tomographic images of these large low shear velocity provinces, but in fact, you actually see it already in the data themselves. You don't have to do any tomography to see it. You compare the travel times of waves that sample the base of the mantle and waves that don't sample, like the wave S and the wave SCS, and you compare, you do the difference between them and you project it on a map, and you already see the large low shear velocity provinces. You don't have to do any magic, any complicated inversion. It's right there in the data. So when you do this difference, you get rid of everything else in between, from the surface to just the range of depth where the the two waves do not have the same path. So I don't think we're going to be surprised. I mean, I think the large low shear velocities provinces are there to stay. Any tomographic work in the last 20 or even 30 years, because they were discovered already 30 years ago, has confirmed them. What is in store for what we have to determine is their fine scale structure. Are they a bundle of plumes, or are they compact features? And the debate is there right now, and I'm on one end of the debate, because in our models our models seem to indicate that they are more like a bundle of separate plumes that are separated by the graveyard of slabs falling in the mantle. But this needs, of course, to be, this is a debate right now. So we may get surprises on exactly the fine scale structure, but the general configuration is not going to change, I think.
Thank you very much, Barbara. And as I said, I really want to echo the many messages that came through. Thank you for an excellent presentation, and thank you for your time. This hour went way too fast, and the connection was superb as well. So thank you very much. And
thank you.
That at some point we can redo all of this again. Thank you very much.
So I should unshare my screen.
And this will take us into the second part of our session this afternoon here from Vienna. We have another hour of a presentation, this time by Paul Richards. This is an invited talk. It's the first invited talk on the 25th anniversary for the opening of the CTBT since for signature. And of course, if you have managed to either be in the Hofburg yesterday or you streamed the proceedings from there, you would have heard that, of course, since 1996, we are now 25 years later, and we'll be using this opportunity to look at examining the developments and achievements since 1996, and also the prospects for the future. So Paul Richards is not here in Vienna, unfortunately. He is in the US, and I imagine, Paul, it's still quite early in the morning. So let me introduce you by saying that Paul has taught at the Columbia University since 1971, where he's conducted research on the theory of seismic wave propagation, physics of earthquakes, the interior structure of the earth, and the application of seismological methods to explosion and earthquake monitoring. He's a co-author, I don't even think I should say this, but a very well-known text, of course, of the quantitative seismology. I believe it is available apart from English in Russian, Chinese, and Japanese. He's a co-discoverer of the evidence for superrotation of the Earth's inner core. He's been Emeritus Professor of Natural Sciences since 2008 and is currently Special Research Scientist at Columbia. He's held the Guggenheim and MacArthur Fellowships, chaired Columbia's Department of Geological Sciences from 1979 to 1983, served terms as visiting scholar at the U.S. Arms Control and Disarmament Agency in 1984 and 1993, respectively. He was elected to membership in the Council of Foreign Relations in 1992. He participated for the United States in Geneva in the CTBT negotiations and is a fellow of the American Academy of Arts and Sciences. In 2009, he received the Seismological Society of America's highest medal for outstanding contributions in seismology. Paul, very welcome to our session this afternoon, and we're looking forward to your presentation.
So, thank you, Gerhard, for that introduction. Can you wave a hand if you can hear me?
Absolutely.
Thank you, good. And first, let me say to my friend, Professor Barbara Romanovitz, what a wonderful presentation. showing how much we are currently able to understand of phenomena on our magical planet. I did hear you say that body waves at short period are much more challenging to interpret, and I agree, but we are making progress, as I hope to explain in my own presentation. I have been asked to talk about monitoring methods, noting that this is mostly going to be about seismology, and I have two main goals. I want to talk about some of the newest work, and I want to convey the importance of some of the oldest data. So let me begin with a screen sharing process. And at this point, yes, this shows my main, introductory graphic. And moving on, here is a CTBTO graphic showing the history of nuclear tests, the number each year as a bar chart above ground or below ground, as appropriate for atmospheric and in space explosions compared to underwater, underground. And of some interest is another way to present these numbers, of course, noting that they have come almost back to zero. No tests since 1917. But shown here are in red the large number of nuclear explosions conducted in the era of old style recording, whether analog tape or analog paper, and note some of the numbers. For the United States, for example, those red numbers add up on the top line of the US row to more than 850 nuclear tests, and then the next line, more than 540 by the Soviet Union in that era dominated by analog recording. In this period were conducted all test explosions in space, in the atmosphere and underwater by these countries, and most of the underground tests. So how has the work of monitoring changed over these decades, moving from red to green numbers, the era of digital recording, and ever more sophisticated methods of analysis? And gradually, we are moving towards a time where in the columns you see many zeros. No nuclear tests, as I just said, for the last 4 years, none at all. And so what has been the overall change over this time period in methods of monitoring? Well, at this point, perhaps you in the audience could reasonably ask, who is this guy speaking? And I should emphasize that I am an academic. I'm a professor. I work in a university. I speak for no agency. I was born in the United Kingdom, but I've lived for most of my life in the United States. I don't have to ask for permission in what I say. And the other good concept is that you don't have to listen to me because I don't represent any agency. I have been involved, however, in some writing. As you see it here in 1988, I wrote some chapters in a report for an agency of the US Congress in 1988, when all monitoring was done at great distances. We call it teleseismic monitoring in seismology. And then in 2002, for the US National Academy of Sciences, I drafted all the sections on monitoring as the CTBTO was getting started. And then I was part of a writing team on this one, the third one on the right shown here for 2012. What changed in these 24 years is shown here in a graphic that goes back probably to Carl Romney, who made it in about 1960. And what we do today is monitor what we call regional waves in seismology, typically larger than those waves recorded at great distance beyond about 1,500 kilometers. The teleseismic waves emerge at great distance after going at great depth in the Earth. These regional waves out to about 1,000 kilometers or so, they show great variability in the Earth, but are associated with propagation in the upper levels. And at this point, as I start to get into the technical area, perhaps this is a time for me to speculate that in this audience, I have probably most people who are not experts, but I know this audience most definitely has world-class seismologists, and I hope I have something for you too in what I'm trying to say here. So let me quickly go through back to the basics, review the 6 different steps in explosion monitoring, where we need to detect signals. We need to gather all the signals that come from the same source, a process of association. I will be mostly talking today about this 3rd step. Where were these detected seismic events? Others, of course, the later steps involve an identification, what type of event, what country is the region where they happened. And then for some people, important is yield estimation. So I then want to say that we need to do this work in 2 different ways. Are we monitoring in the context of nuclear tests carried out, as most of them were, more than 2,000, without any attempt to conceal them? Or might there be some evasion attempt? And what constitutes an adequate level of monitoring? Who decides? That's not the seismologists or technical people to decide, but certainly it's our responsibility to provide appropriate input where we can. So let me at this point go to the question of location. And I'm going to go quickly through the method of location that by far is the dominant method, and it has been used for well over 100 years in seismology. And this is derived from an IRIS website, a website showing how to locate an earthquake or an explosion with data from 3 stations in the United States. The nearest is Tucson or Wallace, Cathedral Caves in Missouri. And each of these stations makes a record of an explosion. And this is a typical record. And the words P and S, to remind you, simply stand for the primary, the first arriving wave, secondary, the second arriving wave. The next station, a little bit closer. Because it's closer, the P waves and the S waves, primary and secondary, are not so much separated in time. And then at the closest station in Tucson, Arizona, only 85 seconds separates the 2. And the point is that if we can translate a time measurement to a distance from CCCM, from COR, from TUC, where these 3 circles intersect is a location estimate. Now, I want to say that this is really ridiculous. Earlier today, I heard David Bowers describing how Sir William Penny, in the negotiations of the late 1950s and early 1960s, referred to seismology as a Stone Age science, because there are 3 dreadful flaws in the location method that I've just described to you. Here they are. It uses only a small fraction of the information in seismograms. It is based on information taken from where the signal is small, the arrival of P waves and S waves, and it requires a method to convert the measurement, which is time on the seismogram, to a distance, for example, to get the radius of a circle centered on each station, and the conversion factor from time to distance is different for different regions. However, the dominant method for locating earthquakes by the International Seismological Center, by the United States Geological Survey with its preliminary determination of epicenters, and with the reviewed event bulletin and the late event bulletin, and many other agencies around the world, use basically these methods. They are somewhat improved. I tried this myself, and others have continued much better with the development of station corrections that are different for different source regions to help address the last bullet to get a better method of converting from the measurement of time to distance. But still, there are these earlier two bullets. So I don't perhaps make myself very popular in pointing out these three flaws of the dominant method, but I want to indicate how we can overcome them and to give an overview of seismological capabilities to monitor for nuclear testing in the DPRK. So for monitoring in that part of the world, not only do we have the contributions from the International Monitoring System and the International Data Center, but there are regional organizations, most notably, of course, China and Japan, with thousands of seismometers. The Republic of Korea also has an extensive network. There are international organizations that do global research, and bringing these resources to bear on the seismic events of the DPRK, we find that we can detect underground explosions, and in recent years, their aftershocks, down to very small seismic size. Here are some of these resources. The test site in North Korea, shown here is an open station in Manchuria, an IMS station. We have some data for a period of 6 years, just north of the border with North Korea. And my point is then that in the work of monitoring, for North Korea, to remind you, 6 nuclear tests in 2006, 2009, 2013, 2 in 2016, and then the largest by far, these seismograms are all recorded with the same amplitude at an IMS station in western Kazakhstan. The last explosion intensively studied, not only, of course, by the agencies with prime responsibility for monitoring nuclear explosions, but it's been very interesting to see numerous papers published by earthquake specialists working in China, in Kazakhstan, and in many other countries, studying this very tightly regionally confined area of not only nuclear tests, but in recent years, their aftershocks. We have information released in a brief period of openness of where these 6 tests were underneath Mount Tap. And I want to summarize the location aspects with this map showing with stars the location of the first test of the 5 directly under Mount Tap. And remarkably, even down at magnitudes in the level of 2.5 to 3.5, aftershocks of the largest test, a few kilometers to the north and slightly to the west. So this work was done by using regional waves, not working just with the time of first arrival, but with the whole shape of the wave, and most particularly with the regional wave where it has its maximum amplitude, as recorded at stations in Manchuria and stations in the Republic of Korea. And there you go. Yeah. Okay. So I showed this diagram before. To use for location, not the places where the signal is weakest, and to measure time of arrival, and that's the only information, but to look at the place where the amplitude is largest. Now, I worked for more than 30 years in my career as a theoretician. My first degree was mathematics, and the textbook that Gerhard mentioned in his introduction of me, I counted electronically. That textbook had 6,000 uses of the equals sign. So it has equations. Maybe it only said x equals 0, but sometimes it was a more formidable formula. But although I have those theoretical trainings, in the last 20 years, I have become more and more interested in empirical methods. Perhaps this is from working at my institution, the Lamont Doherty Earth Observatory, which is a data-based institution, but also in recognition that unfortunately, the potentially most informative part of this type of seismogram, where the amplitudes are so large, what Barbara Romanowitz described as the short period, well, body waves, but waves trapped in the Earth's crust, we don't yet have an ability to compute the shapes of these signals in great detail up at high frequency. But what we can do is compare the waveforms of two neighboring seismic events as measured from the seismograms at a station that recorded both those events. And we can measure with subsample precision the slight difference in arrival time of the signals from two events, and thus get some constraint on their relative distance. Do that at enough stations that recorded both events, and we can get their relative location with precision that can be measured in fractions of a kilometer. So I'm talking about waves. Here is the so-called love wave in the granitic layer, the LG wave, trapped in the slow velocity Earth's crust. Many multiples create that largest amplitude signal. And the overall physics is very much like the way that an optical fiber efficiently carries light to great distances. So let me say that these high precision methods, which I very quickly reviewed for the People's Republic of North Korea, Democratic People's Republic of North Korea, work very well, as was first demonstrated, for example, in Iceland, where a lot of these methods originated for small regions. And 2 years ago, we had a presentation with my colleague David Shah, who has contributed so much to the improvement of the methods I'm describing, asking the question, can they be applied to broad areas? We got a start in 2019, but we weren't really able to deliver the results that I'm very happy to be presenting now. And in recent years, we have had a focus on the seismicity of a large country, Mongolia, to the north of China, but not just Mongolia. And some details of what I am going to summarize shortly will be expanded when David Schaff gives a presentation tomorrow with this title. So I am using some of his graphics. And let me talk about the overall method that we have developed in a series of 19 papers over the last 6 or 7 years. The modern methods of event location that achieve, in my opinion, the potential for a breakthrough in earthquake and explosion locations that work best in regions where there are lots of events, is to identify well-recorded events and use their signals as templates. Pull out those waveforms as templates is the second step, and then run those templates against the continuous archive for a number of stations. And in the present case, we did that for a 5-year period, using a method that declares a detection of a new event with the same waveform shape, sufficiently similar to the template to have a high cross correlation value, and make that detection on the basis of a predetermined choice of false alarm rate. To validate these detections by seeing if they're seen also at other stations, to measure the relative arrival times with subsample precision, and then to locate as many events as possible. So let me talk about this work, recognizing that a lot of people have contributed. I pulled out some names here. Felix Waldhauser, Won-Young Kim at Lamont, and more recently, Göran Ekström. And it's wonderful that Rosalie Lopez, with much assistance from Megan Slinkard and Amy Sundermeyer, that this work, which is computationally intensive, is not like artificial intelligence or machine learning, because the work is done on the basis of many choices that have to be made, and they're made by experienced analysts on the basis of careful examination of test areas where we build knowledge of how many seconds for the time window, what bandwidth to use, and so on, what signal to noise levels work adequately. So the area to which we've applied these methods is not just Mongolia, but it's internal to the green line you see on the screen. It includes large parts of southern Siberia in the Russian Federation, most notably including the Kuzbas region of major mine blasting and the Altai Sayan, large regions of Kazakhstan, of China. And you see here from the text about using about 1,000, let's get rid of that, master templates from the late event bulletin, running with 5 years of continuous data, finding about 33 times as many smaller events were successfully pulled out by the cross-correlation detector, but unfortunately not at enough stations to get an adequate location. Most fortunate for us, and it was done with some degree of forethought here, is the fact that in the same 5-year period, a research project led by Lehigh University in Pennsylvania in the United States deployed more than 40 Pascal instruments whose data is openly available from the IRIS data center. It would be good also to work in this mode with stations from the Mongolia National Network, from other stations as may be available in Siberia, China, and Kazakhstan. But in order to locate the 33,000 events detected by templates run against the continuous archive, David Scharf made a very sophisticated data quest data request, not for the continuous data from these more than 40 stations, but a segmented data request of a 5-year period in order to use 50 seconds of the LG window for 33,000 events at more than 40 stations over a 5-year period. And the outcome is a series of clusters, many of them in the Kuzbas region. And now I'm using some of the graphics again that David Schaaf will discuss in more detail tomorrow. And many clusters, in some cases, hundreds of events in a cluster. The largest had 6,000 seismic events over the 5-year period. On the left, we see for 12 of the clusters, the time of day in local time at which the seismic event occurs. And if you have good eyesight, you see with these bar charts showing the number of events per hour in each cluster, that most of the events occur within the green lines from 9 o'clock to 5 local time. 9 o'clock to 5, they're highly concentrated in the working hours in local time, or we can, with the same 12 clusters, look at the day of week, running from Sunday, again, bar charts, the 7 days of the week through Saturday. Yes, different practices for different operations. Here, one with very little on Saturday or Sunday. These people work 7 days a week. So you get the point. The next set of 12 clusters, 11 of them, again, have all of the time distribution in time of day or day of the week that would be expected for a mine blasting region, but this one is more like an earthquake. And so we would go on to show for this region, which truly is a vast region spreading over more than 45 degrees in longitude and more than 10 degrees in latitude. In blue and red are clusters where 75% or more occur in local working hours. In cyan, clusters where fewer than 75%. Well, it turns out that in this area in 2012, there was a significant earthquake, magnitude 6.9. So we are just beginning to get these results. I am interested both in the earthquake and explosion signals. In using the Pascal deployment to have enough measurements of relative arrival time of pairs of events in a cluster, David Schaaf, the graphic of his that he'll explain in more detail tomorrow, is here shown, where the cluster from the LEB collapses to a very tightly regional area. And then Josely Lopez, a baccalaureate student working with us, has gone to these locations, and with Google Maps, we find, surprise, surprise, yes, these are overhead views of obvious mining regions. I will go through several of them. All these red dots are clustered activity discovered seismically by using methods that we're beginning to learn how to apply over broad areas. And in the present case, 4 different clusters, but all of them in general in mining regions. So I want to make a just broad point here that people who are describing the good work at the IMS and the IDC can obviously be tempted to present their analysis as highly complicated. Success comes only from enormous effort. I remember on the plenary session at the end of S&T 2019, our executive secretary, Dr. Zerbo, noted that the IMS is now acquiring about 14 terabytes of data annually. So it is a big operation. And the achievement is that the CTBTO draws appropriate attention to events which member states can choose to study in greater or lesser detail. And my point overall for the last, I guess, 20 minutes has been to say that intense efforts can then be brought to bear on events of particular interest as deemed necessary. Let me make a few more general points. Well, I'll add this one. That last line I've added in boldface, that many assets can be used. The type of work that I've been describing mostly so far in this presentation really relies hugely on a main data product, in our case, the LEB from Vienna, because we need to know where to start. Where do some plausible templates come from? Where are they likely to be found? So we go to the LEB and get signals from the events that are already known. And then off we go. We can start to use modern methods, highly informed by expert analysts, to detect additional events. And I have emphasized the work of location and have shown that large numbers of seismic events can successfully, with minimal analysis, be shown to have the characteristics, at least in their time of occurrence, of being the result of a working mine with commercial incentives to operate in, broadly speaking, a dangerous environment, to operate in the competitive world. Let me give you some numbers about the mining industry. I remember when I studied it intensively as a lead-in to the negotiations of the CTBT text in Geneva in the 1990s. In the United States, mining was an $8 billion a year enterprise, which used about 2 million tons of explosives a year. Several other countries, Australia, Morocco, certainly Russia, at the million tons of blasting agents a year were thought conceptually, perhaps, to have the potential for generating so many signals on a high quality seismic monitoring network that the network and the analysts working from it would potentially be overwhelmed by all the mine blasting signals. Well, even the most crude analysis of time of day has been so useful without getting into the details of more sophisticated discriminants of PDS, spectral ratios, and so on, which I could happily talk to you about for 6 hours or more, are not really necessary. So many assets can be used for the purpose of characterizing at least one important attribute of all these seismic events. I'll make another broad point. Almost all my discussion in this presentation has been about explosions, a few nuclear, and many, many, many mine blasting explosions. The type of work that I've described for the last half hour, especially of modern methods of location, is profoundly important in the study of earthquakes, because earthquake clusters and understanding lineations in some detail, especially to interpret patterns of seismicity, which not always, but occasionally may have the potential for leading up to, I will say, the indications of a larger, later earthquake. Over time, the study of patterns of seismicity and understanding causative interpretation of an earthquake bulletin is one of the most important issues in understanding the occurrence of earthquakes. How an earthquake, when it happens, changes the stress and its environment, and stress can build up and up and up over a larger region, and eventually a large earthquake occurs, has to be one of the driving imperatives in the organization of all those agencies using seismology for the study of natural events. So I will go on to describe one other aspect of the overall steps in monitoring for explosions, and that is the work of monitoring for earthquakes, for the yield of nuclear explosions. Many different types of yield estimate. It matters to some people. Of course, it's not directly a technical issue in the Comprehensive Test Ban treaty context, but it is still interesting just to characterize the capability of a network. I remember in those negotiations in Vienna when the concept of a primary and auxiliary network began to emerge. The original goal was that it would enable monitoring down to 1 kiloton, not evasively tested. It turns out we can do even better. Well, the best methods of yield estimation are highly intrusive, using radionuclides obtained from drilling back into the cavity. And then there are seismic methods. And I do just want to comment a little on the seismic methods because I would love to see seismic yield methods for estimating the size of an explosion improve. But just like there are certain fundamental problems in how seismic events are located by current methods, it turns out that there is a fundamental issue with seismic methods, namely, what is the fraction of the yield that goes into seismic energy? And the best way to look at that is to look at some of the figures in an important textbook by Vitaly Vasilievich Adushkin and Sasha Spivak, who published a book that has now been translated as a technical report and is available in English. And here is one of their figures showing a cross-section of Gora Degelin Mountain on the Semipalatinsk polygon after the conduct of an underground 12.5 kiloton nuclear test. And shown in this shading is the seismic velocities after the test as inferred from numerous drill holes going through the mass of the mountain into the zone of a cavity and a chimney and the crushed zone. And remarkably, from the light granite of that mountain with its natural P-wave speed in the range of 3.6 to 4.5 kilometers a second, for a vast region, we see in the volume of the mountain a crushed region, a zone of inelastic deformation. And that is where most of the energy goes. That is where most of the yield derived from the nuclear tested device ends up. And seismology has to work only with the fraction of energy that gets out into elastic energy and radiates away either teleseismically at a certain period range or at regional distances, again, still observing in the elastic region. And if we don't know what that fraction of energy taken out of the original yield was, and we work with only that fraction of yield that gets into seismic energy, well, then absent any calibration of the seismic method, history shows that it is quite an adventure to go to a brand new region and come up with absolute yield estimates based on seismology. We can do it. We typically have to make assumptions. We often have to do it with every help we can get towards calibration. And I appreciate the chance to briefly mention that. So I've emphasized 2 points. Location, we can do it really well. We can apply it now to large clusters of explosives from mine blasting. There's the potential for application in the study of earthquakes. And I had some brief comments on yield, but I think it's time for me to stop, and I welcome any questions on what I've tried to say.
Thank you very much. I will thank you very much, Paul, for the presentation. And as always, you kept us intrigued and wondering what's coming next. So I want to go to a couple of questions that already came in. The one I'm going to interpret a little bit is a question about smallest magnitude that could be found using this method. I think it may refer to the slide that you showed on the cross correlation where you said that many more events could be found through cross correlation than I think with the usual analysis of the seismograms. Maybe some thoughts on that, and in particular, how can we really use cross correlation for different types of events, meaning natural, man-made, and so on?
Yes, well, how to give just a short answer. That's always my problem with a perfectly good question like that. It really depends on what the time scale is for you to give an answer. So let me make first a general point that there are many types of bulletin of seismicity. Some agencies really need to come up with a description of all the seismic events that have recently happened in a very short period of time. I can't remember with the REB, is it on the order of 3 days or less than a week anyway? The late event bulletin may be a little bit more relaxed. Always, if you allow more time, there is the potential for more information to come in. I would go on to say that if there is intense interest in a particular region of space and time, then even over a period of years, people will study a region. And the best example of that, which I can give you, was for the year 2010, when a number of days in April and May of that year were deemed of particular interest because they were associated with a radionuclide anomaly. And at last I can give an answer to your specific question, because in a first study that I did for seismic events in that time period, we found with some level of confidence using stations then available to us, which included an open station in Manchuria at Mudanjiang, that if there had been any seismic event, it would have to have been below about, I think we said magnitude 2, in order to have been not observed. Well, that's a very specific answer to your question. And then, remarkably, a year or so after that publication, was found a seismic event in approximately the right time window, and it was announced by Lianxing Wen and Mao Jiang as having magnitude approximately 1.4 and a high quality recording of that signal didn't show up, in other words, for years after the event. So even down at these low magnitudes in a very small area. So can you appreciate that the answer to your question really brings out the fact that in seismology, it's almost like dealing with Maxwell's equations. Light is everywhere, electromagnetic waves. We have them across an amazing range of wavelength and period, color, size, amplitude. And the fact is, there are thousands of seismometers operated around the world for different regions. And over a period of time, if it really matters, we can find sometimes, maybe not as quickly as we would like, the signals of interest. In the case of the long example I've given you of a seismic event, which did occur on May the 12th, 2010, near the North Korea test site, the data was of such high quality that a team of us who analyzed it were firmly of the conclusion that its P to S spectral ratios were like those of an earthquake and not of an explosion. So that's a long story, but it pertains even down to very low magnitude in that particular case. Another general point to make is that if we accept that this concept of cross-correlation and working with archives is important, there are many implications for how seismology should be organized, because over time, it is the archive which becomes the main resource. And the question of what archives are open and what archives can become open for a particular time period is of enormous importance. So excuse my long answer, but there are so many issues here, but overall, there are huge areas of possibility for future improvement.
Thank you. Thank you very much, Paul. Indeed, I think you actually led right into another question that relates exactly to this about archives. So you showed in your slide the greater number of tests in the pre-digital era. So how important do you think it is to actually get access to this data as it relates to the CTBT efforts right now?
Well, I happen to think it is enormously important. When we look at the amount of resources currently going into the deployment of new stations in interesting places for perfectly worthy goals, I've got no problem with that. I would dearly love to see 1 or 2% of those assets dedicated to the goal of not only preserving, but making usable the archives of previous analog recordings of nuclear test explosions. The fact is that the agencies involved, whether they are primarily studying earthquakes or primarily studying explosions, are different in different countries. Maybe be very interested in the explosion signals coming from a different country, but not so interested in helping to bring out into the open the nuclear test explosion signals of events conducted on the home territory. So, the question doesn't have an easy yes or no answer. It's different for different countries. But over time, and these things can change very radically. If something happens that scares a large fraction of humanity, then suddenly we might see a move towards greater interest in the goals of the Comprehensive Test Ban Treaty, just as happened in 1962 and 1963, and a sudden motion which produced the partial Test Ban Treaty of that era.
Thank you. So we have a few minutes left. Paul, you spoke about yield estimates, and of course one sees the huge uncertainties whenever we talk about yields. We've seen it of explosions. You think that that there will ever be an approach to actually have a more accurate assessment of this fraction of the energy that goes either into the air or into the ground? You think there's anything in the near future that may give us a bit more clarity?
Well, that may be a priority for some people. I think there are things which can help. Certainly, working with those old signals to improve the characterization of events in the past, using them, and it will be different for different countries. But whatever experience can be brought into the open about drilling into underground regions where vast amounts of nuclear energy was converted into vaporizing and melting and crushing rock, that would be of interest. That perhaps is not currently a focus. I see a focus currently on using large chemical explosions sometimes for calibration. And I appreciate that that is an activity important economically for some regions. I have no reason to speak against it. For me, the priority is to improve our access to data of past nuclear tests. They're very different from chemical explosions, which don't put so much energy into damaging the rock, and making those old seismograms usable by the modern generation of analysts. And finally, to say that one difficulty here is that the generation of people who even know about those archives, for natural reasons, is diminishing year by year. So we don't have a lot of time left to save what I regard as one of the most important archives, not just for monitoring, but for all of geophysics.
Thank you, Paul. There was earlier on a question that I think was sort of hinging on the also the ability to detect explosion or tests. I think in this instance, particular nuclear tests that are deliberately hidden. So in other words, clandestine.
Yes.
And I think decoupling is one method. Maybe a last few thoughts around that in the efficiency of
Yes, thank you for that question. So I have been on a couple of panels that met many times with people with vast experience in the conduct of nuclear test explosions. The most knowledgeable person with whom I spent a lot of time on that subject was Harold Agnew, who was the third director of Los Alamos. And on a panel working with him, I was on two separate panels, he came up with the concept from his perspective as a person leading the effort to get scientific information out of nuclear testing. And he spoke of the layers of difficulty in his job of conducting an explosion for purposes of nuclear weapons development. And the cavity decoupling scenario is, in his words, a nightmare. So there is extensive discussion that he originated on the concept of layers of difficulty. You have to have a region with appropriate geology for cavity construction. It has to be remote and controllable. The last place you want to go is a mine-blasting region where there are hundreds of technical people making their own seismic signals. They will find that the seismic signals of a nuclear test are utterly different from the signals of a mine blasting conducted over many decades. So it's not just a matter of anybody can build a hole, put something in it that can go bang and hide it. It's much more complicated than that. And the layers of difficulty led Dr. Agnew to agree with the conclusion of the panels on which he served that you cannot do this work of hiding an explosion reliably if its yield is larger than 1 or 2 kilotons. That's the end.
Thank you very much, Paul. And I want to remind the participants that they can continue to post their questions in this chat room, or also, of course, directly to you, that if there's anything else that they would like to bring up, or to Barbara, that it's still possible. And again, let me reflect the appreciation of the audience today, both Paul and Barbara. We appreciate your time and the excellent presentations that you have made. The 2 hours went, I think, far too quickly, but it's unfortunately time to bring this session to an end. Thank you to you, Barbara, and everyone that participated today, in particular also all the support that we've had here in this room in Vienna from all the WebEx hosts and everyone involved at the technical level. Thank you very much.